Lesson 3, Velocity and Acceleration. In this lesson, we're going to be looking at the connection between displacement, velocity, and acceleration functions and their graphs. So mainly what that means is, in relation to calculus, we're looking at a function, its first derivative, and its second derivative. And we're looking at the connections between those three things algebraically and graphically. This is a super important lesson to understanding calculus, so make sure you take the time to fully understand these concepts. It'll really help you as we move forward in the course. I guess we should start with, what is the second derivative? We haven't even done that yet in the course. A second derivative, simply put, is the derivative of the first derivative. The second derivative of a function is determined by differentiating the first derivative of the function. So let's practice calculating a derivative using the rules we know so far. I think we only need the power rule to differentiate this function here. And then after we find the derivative of that, we're going to then find the second derivative. We're going to calculate f double prime of x. That's how we denote that we're finding the derivative of the first derivative. So example 1 says, for this function f of x, let's start by calculating f prime of x. Let's calculate the first derivative. So you will use the power rule that we've learned earlier in the course. So f prime of x is equal to, take the exponent, multiply it by the coefficient. 3 times a third is 1. Keep the power of x, but reduce its exponent by 1. So we have 1x squared. Now let's differentiate this x squared term. So I'll subtract the derivative of the x squared term, which would just be 2x. Then I'll subtract the derivative of this term, which is just 3. And then I would add the derivative of the constant, but the derivative of any constant is 0. So here's my derivative function. It's in standard form. I notice in part B, I'm going to be solving for when is the derivative of 0. So it may be helpful to actually put this in factored form as well. So we have our standard form version of the derivative there. And here's my factored form version. What multiplies to negative 3 and adds to negative 2 are negative 3 and positive 1. There's two different versions of the first derivative. Part B says, when is the first derivative 0? Now, this is actually a really important thing that we're going to be solving for a lot in this course, because that will tell us what a critical point of the function is, which will identify a possible max or min point on the function. And we'll talk a lot about that throughout this lesson and throughout the next unit as well. This is kind of just an intro to that for you. So when is this first derivative 0? Set the first derivative to 0, and I'll set the factored form to 0 because that'll be easier to solve. And solve this equation. So that equation is 0 if either of the factors is 0. So if x minus 3 is 0, or if x plus 1 is 0. So we have two answers. Our first answer would be 3. Our second answer would be negative 1. So there are two x values that would make the first derivative be 0. And those reveal to us important parts of the graph of the original function f of x. And we'll talk about that as we go. Part C, this is our second derivative we're calculating. If we want to find the second derivative, what we're doing is we're finding the derivative of the first derivative. So we just have to differentiate this function. And I could differentiate either version of it, I'll get the same answer. But the first version in standard form is easier because then I can just do my power rule. I wouldn't need to use product rule. So f double prime of x, we differentiate this function. Take the exponent, multiply it by the coefficient, I get 2. Keep the power of x, but reduce its exponent by 1. Then I'll subtract the derivative of 2x, so minus 2. And then I would subtract the derivative of 3, which would be minus 0, which I don't need to write. So we have 2x minus 2. That's standard form. Once again, maybe you would want it in factored form. Doesn't really matter. I'll write it just in case you would want that. It would be 2 multiplied by x minus 1. When is the second derivative 0? This tells us where a possible point of inflection is. Now, you don't know what that is yet, and that's fine. We'll talk about that more as we go. But when the second derivative is 0 also tells us something very important about the original function. So let's set the second derivative to 0 and solve. I'll set the factored form to 0, doesn't matter. This product would be 0 if x minus 1. This product would be 0 if x minus 1 was 0. And x equals 1. So an x value of 1 makes the second derivative 0. We're going to look at the graph of the original function and make a connection between the graph of that original function and the graph of its first derivative and the graph of its second derivative. And you're going to find out that these x values we solved for, 3, -1, and 1, where the first derivative is 0 and where the second derivative is 0, actually are very key points on the graph of the original function. So here I've given you the graphs of f of x, f prime of x, and f double prime of x. So I've given you all three graphs if you're following along in the lesson. We want to find the connection between all three of these graphs. So ideally, by the end of this lesson, you're going to be able to look at the graph of the original function and then be able to determine what the graph of the first derivative and the second derivative would look like. So it's going to be helpful for me to move over to Desmos for a minute here and get us to start analyzing the values of these functions algebraically and how that's going to help us determine their graphs. Okay, here's the original f of x function. I've color-coded it. Part of it's blue, part of it's red, part of it's blue. I'll explain why in a second. But what I have here, I have Desmos allowing me to sub x values into the function. So my x value right now is -1, and then what I have Desmos doing is I have it calculating the value of the original function. So the y value of the original function is 5.7-ish. It's up here. I also have it telling me what the value of the first derivative is at that x value, and what the value of the second derivative is at that x value. So my goal for this is to explain to you the connection between the graph of this f of x function and the graph of its first derivative and the graph of its second derivative. So while I'm explaining, I need you to be paying attention to the values of the original function, f of x, the value of the first derivative, f prime of x, and the value of the second derivative, f double prime of x, for all of the x values that I have it plugging in. So let's look at why do I have it color-coded in this way first. What do we notice about the y values of the original function and the y values of the first derivative in the blue section? So keep in mind the first derivative tells us the rate of change, the instantaneous rate of change, of the original function. So basically it tells us how the original function's y values are changing. This number tells us how these numbers are changing at any one instant in time. The second derivative tells us how the first derivative is changing. So this number tells us how these numbers are changing. But right now let's just focus on the first two pairs. Let's focus on the f of x value and the f prime of x value. So let's look at these numbers as I drag this point along the function. Let's look at these y values. Let's look at this first blue section. Right now, the y value of the function is at -7. Now it's at -6. Now it's -3, -1, 1, 2, 3, 4, 5. It goes all the way up to 5.7. And then after that x value, the y values start coming back down. They come down to 5, then 4, then 3, and so on. So do you notice in this first blue section, the y values of the original function are all going up? The original function is increasing for x values less than -1. Now let's pay attention to what the first derivative values are in that section. 12, 10, 8, 6, 3, 1, and so on. So the main thing I want you to notice there is the values of the first derivative are all positive. All of these tangent slopes in this section are all going up to the right, which means they're all positive. A positive tangent slope, so a positive value of the first derivative, tells us that the original function is increasing. It tells us the rate at which it's increasing, and that rate is slowing as we go, but we'll leave that until we start talking about the second derivative. So right now, a positive value of the first derivative tells us the original function is increasing. In the red section, so for x values between -1 and 3, let's look at the y values of the original function. They're at 5.7. They go down, 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 down. The y values keep going down. They're at -1, -2, -3. They go as low as -5. Since the y values of the original function were going down over that interval, that tells us the original function is decreasing. which means all the tangent slopes would be negative. Look at the value of the tangent slopes, the value of the first derivative. They're all negative. And then in the third section, this section for x greater than 3, the original function is increasing. The y values are going up. That means the tangent slopes are positive. That's why you'll notice the first derivative in that section of the domain is always positive. What happened at an x value of -1 and at an x value of 3? Did you see what the value of the first derivative was? Well, look at an x value of 3. That's a local min point on the function. That's where the function is not decreasing and it's not increasing. It's where it switches from decreasing to increasing. Look at the tangent line. It's completely horizontal. The slope of a horizontal line is 0. So do you see how figuring out where the first derivative is 0 can help us figure out where local max or min points are? Because it tells us where a point on the original function has a horizontal tangent. Also look if x was -1, put the tangent line there, value of the first derivative 0 as well. So if you have a turning point, the slope of the tangent there would be 0. So if we can figure out where the first derivative is 0, we have found where a potential local max or min point on the function is. All right, let me throw up the graph of the first derivative now. So notice whenever the original function is increasing, the first derivative has positive y values. And do you get that the y values of the first derivative tell us the tangent slopes of the original function? So for example, let's move x to -2. If x is -2, the original function's at 3.33. It doesn't really matter where the original function is. Where's the first derivative when x is -2? It's up here. It looks like it's at 5. Why is it at 5? Well, because what's the tangent slope on the original function at an x value of -2? Well, it's asked Desmos. It says, oh, it's 5. That's why the first derivative is up there at 5. It tells us the tangent slope, the slope of the original function, at any one point. In the section between -1 and 3, the tangent slopes are all negative, which is why the first derivative in that section is below the x-axis. All the y values on that section would all be negative. And then when x is greater than 3, the tangent slopes are all positive, which is why the first derivative has positive y values in that section. So quick summary, if the original function is increasing, the first derivative has positive y values. If the original function is decreasing, the first derivative has negative y values. And then once again, the original function switches to increasing, which means the first derivative has positive y values. Okay, if you got the connection between the original function and the first derivative, then you'll understand the connection between the first derivative and the second derivative. Like I said, the value of the second derivative just then tells us how the values of the first derivative are changing. So it tells us how the tangent slopes are changing. Here's the graph of the second derivative. So in blue is the graph of the first derivative, in green is the graph of the second derivative. Let me draw a tangent slope on the graph of the first derivative. So now let's pay attention to what's happening to the first derivative values on the interval x less than 1. Those first derivative values are going down, 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 down. They go down as low as -4. That's the lowest the first derivative values go. And then the first derivative values switch to going up. So the first derivative is decreasing until 1, and then increasing after 1. That means the second derivative will be negative y values before 1 and positive y values after 1. Because the value of the second derivative corresponds to the rate of change of the first derivative. So it tells us what the tangent slope on the first derivative is at any point. And the tangent slope on the first derivative at 1 is 0. That's why you see the second derivative has a y value of 0 when x is 1. Okay, the hardest part of this is then maybe trying to make the connection all the way from the first derivative to the second derivative. This is a little bit harder. So the easiest way for me to phrase this, let me put the tangent slope on the first derivative back. Remember, the second derivative is 0 when x is 1 right here. Pay attention to these tangent slopes on the original function before an x value of 1 and then after an x value of 1. So let's pay attention to this number here. This number here, right now it's 5. It's 5, 3, 0, -1, -2, -3, and it goes all the way down to -4. And then after 1, it starts going back up to -3, to -2, to 1, 5, 8, and so on. At an x value of 1, that's when the tangent slopes stop decreasing and start increasing. So before an x value of 1, the tangent slopes are decreasing. Right? The second derivative tells us how the first derivative is changing. So it tells us how the tangent slopes are changing. The tangent slopes are decreasing. Right? Pay attention to this number here. That number is decreasing until an x value of 1. After the x value of 1, this number starts increasing. That's why the second derivative is negative till an x value of 1, positive after an x value of 1. Graphically speaking, we often say when the second derivative is negative, we say the function is concave down. Notice this function is below the tangent line at all values of x until an x value of 1. After an x value of 1, the function switches, and now the function is above the tangent line. We call that concave up. So the sign of the second derivative, if it's positive, tells us the function is concave up. And if it's negative, as in here, tells us the original function is concave down, meaning it opens below the tangent line. Okay, that's a lot to take in. We're going to spend the next, couple of units solidifying all of this information and figuring out what it's useful for. But this is a good starting point to help understand the connection between a function, its first derivative, and second derivative. Okay, so let's go back to the lesson and kind of jot down these connections. What this says over here, it says the negative y values, and let me just highlight this. The negative y values on the first derivative from here to here correspond to the fact that on the original function, between -1 and 3, the original function is decreasing. If I were to draw a tangent line to any point on that function, between -1 and 3, that tangent line would have a negative slope. That's why the first derivative has negative y values, because the y values of the first derivative tell us the slope of the tangent on the original function. It tells us how the original function is changing at any one point. And then it also says here, the x-intercepts of -1 and 3 correspond to the points on this function that if you were to draw a tangent line, they would be horizontal. So they're local max or min points. Here it's written more neatly. When x is less than -1, the original function has positive tangent slopes, which then corresponds to, on the graph of the first derivative, positive y values. Then here, the original function is decreasing, has negative tangent slopes, so therefore, on the first derivative, it would have negative y values. And in this section, the function is increasing and has positive tangent slopes, which means the first derivative would have positive y values. Here, and here the tangent slopes are 0, which means the y value of the first derivative is 0 at those two spots. Now the connection between the first and second derivative. The second derivative having negative y values in that section tells us that the first derivative must be decreasing over that interval, and in fact it is. And then the second derivative having positive y values when x is greater than 1 tells us over that interval the first derivative must be increasing, and it is. Remember, the second derivative tells us the rate of change of the first derivative. And notice at this point right here, when x is 1, the first derivative is not changing. It has a tangent slope of 0, which means the second derivative would have a y value of 0 at that point. So here it is written neatly for you. First derivative is decreasing when x is less than 1. Therefore, second derivative has negative y values. First derivative is increasing when x is greater than 1, which means second derivative has positive y values. Tangent slope is 0, which means second derivative has a y value of 0. Let's move on to part 2, displacement, velocity, and acceleration. This is directly related to what we were just talking about, the connection between a function, its first derivative, and second derivative. Displacement, remember, is the distance an object is from where it started. And we typically call that function d at t or s at t. Now, velocity is the rate of change of displacement with respect to time. And when you see this word rate of change, think derivative. So it's the rate of change of displacements. That tells us the velocity is equal to the derivative of the displacement function. V at t equals s prime at t. And if displacement is in meters, then that means our velocity is the rate of change of meters with respect to time, so it's meters per second. Now acceleration, well, that tells us how velocity is changing. So rate of change of velocity with respect to time. So the acceleration function is equal to the derivative of the velocity function. And remember, the velocity function is the derivative of the displacement function. So really, acceleration is the second derivative of the displacement function. If we differentiate the displacement once, we get velocity. If we differentiate the displacement function twice, we get acceleration. So hopefully you see this connection between these three terms: displacement, velocity, acceleration. Velocity is the rate of change of displacement. Acceleration is the rate of change of velocity. And I put a note here, common confusion. Now, a lot of people have covered this type of stuff in their science classes, but common confusion is with distance and displacement. Distance would be the total distance an object is moved. We're dealing with displacement, which is the distance an object is from the start, not the total amount of distance something has covered, but its displacement from where it has started. And the other common confusion is with velocity and speed. Now, speed is just a scalar quantity. It doesn't have any direction associated with it. But we're dealing with velocity, not speed. Velocity does have a direction associated with it. Velocity has a magnitude and a direction. It tells us its speed with a direction. The sign of the velocity tells us the direction. So let's go ahead with an example. Example 2, a construction worker accidentally drops a hammer from a height of 90 meters. The height, s, in meters of the hammer, t seconds after it is dropped, can be modeled by this function. So this tells us the displacement of the hammer from the ground. So it tells us its distance from the ground. Let's just look at the graph in Desmos. So here's the function. Now, we're only going to be interested in when time is greater than 0, so maybe I will change the domain of this function here. I'll change it to when t is, or I guess I called it x on here, but in our actual question is t, when t is greater than 0. So let me reset this parameter as well. All right, so there's the displacement of the hammer from the ground. There's the graph. And I have Desmos telling me the value of the displacement, the rate of change of the displacement, which we would call the velocity, and the rate of change of the velocity, which we call the acceleration. So I have it telling us all three values: the original function, first derivative, and second derivative. So if we look at this graph, we can see he drops the hammer from a height of 90, and then that height of 90, as time progresses, that height of 90 from the ground is obviously decreasing, which is why the first derivative is negative. The question says, what is the velocity of the hammer at 1 second and 4 seconds? Well, velocity, if I want the velocity at a certain number of seconds, velocity is the rate of change of the displacement. So I'm going to need to figure out the first derivative of the displacement. So if I differentiate this function, the derivative of 90 is 0, minus the derivative of that power function. 2 times 4.9 is 9.8. T, reduce the exponent by 1. So let's simplify this. It's just negative 9.8 t. And the question wants to know what is the velocity at 1 second and 4 seconds. So let's plug in 1 and 4 into this function and solve for both of these. So we get negative 9.8 meters per second. That's the velocity. So the speed is 9.8. The negative tells us that it's going down. It gives us the direction associated with it. And the velocity at 4 seconds would be negative 39.2 meters per second. So let's have a look here. At 1 second, the rate of change of the displacement, since it's a negative tangent slope, I know the first derivative is going to be negative. It's negative 9.8. And at 4 seconds, The tangent slope is really steep. It's still negative. So it's going to be even a smaller number. It's going to be, now it's negative 39.2. It has a bigger absolute value, but it is a smaller number. It's more in the negative direction. Part B says, when does the hammer hit the ground? So I know, when is the displacement from the ground 0? So this has nothing to do with velocity or acceleration. I just want to know, when is the original function, the displacement function, equal to 0? So let's solve that. Let's set s at t to 0. So if I solve this function, 4.9 t squared equals 90. T would equal plus or minus the square root of 90 over 4.9. Now I actually don't care about the negative square root, because if we think about our graph, that would mean we get this value over here, negative 4.286. We're only interested in this part of the graph, so we would only want this answer, 4.286. And let me just type into you, showing you that this will give us the correct value. We want to do the square root of 90 over 4.9. And that's that 4.286 value. Right here, that's where it hits the ground. That's where its displacement from the ground is 0. We would get 4.286 and also negative 4.286. But we can reject the negative one because we know we can't have a negative time. So at 4.286 seconds is when the hammer is going to hit the ground. Part C says, what is the velocity of the hammer when it hits the ground? Okay, well I have the velocity equation. The velocity equation was negative 9.8 t. I'm interested in what's the velocity when it hits the ground. And when does it hit the ground? At that time. So let's sub that time in for t and evaluate. So v at 4.286 equals negative 9.8 times 4.286. And I'll get Desmos to evaluate this for me. So let's sub in 4.286. The original function is at 0. I mean, there's rounding, so it's a little off, but the first derivative has a value of about negative 42. So it's about negative 42 meters per second. Velocity is in meters per second. It's the rate of change of displacement with respect to time. Part D says determine the acceleration function. Well, the acceleration function is equal to the derivative of the velocity function, which is the second derivative of the displacement function. So let's differentiate this velocity function. That would just be negative 9.8. That means the acceleration is always constant. The acceleration is always negative 9.8 meters per second squared. In this last part of the lesson, we're just going to look at analyzing displacement time graphs and be able to comment on whether an object is speeding up or slowing down in a section of the graph. So all of these functions I'm showing you, these red functions, those are the displacement time graphs. Based on that graph, we should be able to comment on the sign of the velocity, the sign of the acceleration, and then know whether the object is speeding up or slowing down. So these two examples, the yellow parts that I have highlighted, are examples of what a curve could look like if in a displacement time graph the object is speeding up. All right, here's a function that looks similar to what we see on your lesson. And we're going to be looking at two sections. We're going to look at a section that looks like this green part that I have here. Notice that green part kind of looks like this highlighted part. Let's pay attention to the value of the function, its first derivative and second derivative in that green section. Remember, the value of the first derivative tells you how these values are changing, and the value of the second derivative tells you how these values are changing. So the first derivative in this green section, right here, notice those values are always positive. That's because the tangent slopes are always positive in that section. And that's because these numbers, the y values of the original function, as I move from left to right, are all going up. They're all increasing. The original function is increasing. That tells us the first derivative is positive. This is why it tells you in a section that looks like this, the velocity is positive. The function is increasing. Now let's look at why is acceleration also positive? Well, these tangent slopes that we see right here, What's happening to those numbers? Are they increasing or decreasing? Those numbers, as I move from left to right, are increasing. So that's why the second derivative is positive in that interval. Because this tells us, since this is positive, it tells us these numbers are increasing. So if we have a positive tangent slope, so a positive velocity, that is increasing, so if we have positive tangent slopes that are increasing, like look at these tangent lines. As I move from left to right, notice those tangent lines are all positive and those tangent slopes are increasing. So the tangent lines are getting steeper, which means it's speeding up. This scenario over here, this yellow highlighted section, is another example of speeding up. Let's look at why. So I've now highlighted a section that corresponds to that in green right here. So let's look at, in this green section, what's happening to the numbers. The original function, the y values, in that section are going down. So the original function is decreasing. That's why the first derivative is negative. All the tangent slopes in that section are negative. That's why the velocity is negative. The tangent slope represents the velocity. Why is the acceleration also negative? Well, the acceleration tells us how the tangent slopes are changing. And those tangent slopes, like I said, they started at negative, like negative 0.4, and then they kept going down. Now, my question for you is negative 3 less than negative 2? Yeah, of course it is. So the tangent slopes are decreasing. That's why the second derivative is negative. So we have, over this interval, as I move from left to right, we have negative tangent slopes that are decreasing. Those tangent slope numbers are getting smaller. So we have negative tangent slopes that are decreasing. This tells us they're negative tangent slopes. This tells us that those tangent slopes are decreasing. Both of those scenarios are examples of speeding up. The functions are getting steeper in both of those scenarios. And if we do the product of the sign of the velocity and the acceleration and get a positive result, that tells us it's speeding up. Let's look at the other two scenarios. These are two scenarios where the object is slowing down. Let's analyze this shape first. So that I have in green over here. In that section, notice the y values of the original function are increasing, right? The tangent slopes are positive. That's why the first derivative is positive. But what's happening to those tangent slopes? How are those tangent slopes changing? As I move from left to right, this number here, the tangent slopes, the slope of the original function, those numbers are decreasing. So yes, there are positive tangent slopes, but those positive tangent slopes are decreasing. So that means the original function is increasing, but the rate at which it's increasing is slowing. So that's an example of slowing down. Velocity is positive, but acceleration is negative. If we do the product of those two signs, a positive times a negative is negative. That means slowing down. Let's now analyze this type of shape. Okay, it's this green section right here. In this green section, the y values of the function are going down. That's why the first derivative is negative. So that's why velocity is negative. The tangent slopes are all negative. But what's happening to those tangent slopes? Let's pay attention to those tangent slopes as I move from left to right. They go from negative 4 to negative 3 to negative 2 to negative 1. They're increasing. Those tangent slopes are increasing, which means the slope of the function is increasing. So the acceleration is positive. A negative times a positive is negative, which means slowing down. So once again, in both of these two sections, as you move from left to right, the function is getting less steep, which means slowing down. Example 3. The position of a particle moving along a straight line can be modeled by this function where t is the time in seconds and s is the displacement. So we have a displacement time graph of a particle moving along a straight line. Use the graphs of s at t, v at t, and a at t to determine when the particle is speeding up and slowing down. So we're going to fill in this chart using this graph. Now for our first example, it may help if we actually sketch the graph of v at t and a at t based on the graph of s at t. But we won't need to do that for future examples. We should be able to tell just from this function here. So we want to look at this displacement graph and figure out what's the velocity graph going to look like. And remember, velocity is the first derivative of displacement. So we're looking at what is the rate of change of this function. Well, the rate of change of this function here and here would be 0. And that's because the tangent slopes drawn there would be horizontal. They would have a slope of 0. So I know the first derivative at an x value of 2 and 6 would have a y value of 0. And I noticed the original function, the displacement function, is increasing before 2. That means the first derivative is going to have positive y values before 2. It's then decreasing between 2 and 6, which means the original function is going to have negative y values between there. And then it switches back to increasing after 6, which means it's going to, the first derivative would then have positive y values after it. So it's going to look something like this. I mean, that's not a very good sketch, but I have the correct intervals of positive and negative y values, so that'll do just fine. Now, how would I sketch the acceleration graph? Well, that's just the second derivative of displacement, which means it's the first derivative of velocity. So I just have to find, well, what's the derivative of that function look like? How is this function changing? Well, right here, it's not changing. Its tangent slope would be 0. So when x is 4, the second derivative would have a y value of 0. Before an x value of 4, this function's decreasing, which means that this would have negative y values. And after an x value of 4, this velocity function is increasing, which means the acceleration function would have positive y values. So this should look like a linear function. So using these graphs, we could fill out this chart. Oh, and I did them more neatly here, showing you the connection between them. Those are definitely better sketches, so maybe I'll refer to those. Those are just better sketches of what I have here. And notice I also gave you the equations of all three of the functions, so when we have the equations, we could graph them perfectly. But for now, what I'm most interested in is you being able to do this without an equation. But maybe a connection to make. Notice, if the original function is degree 3, its derivative is 1 less. It's degree 2. And when we differentiate a degree 2 function, we get a degree 1 function. The derivative is always 1 degree less. Okay, let's use those graphs to fill in this chart. Now I'm just writing the sign of the velocity and the acceleration function in each interval. So between 0 and 2. So between 0 and 2, the velocity function, I'm looking in this section here, between 0 and 2, the velocity function is positive. And why is that? It's because the original function is increasing. So between 0 and 2, the velocity is positive. Let's fill in this whole row between 0 and 2. Well, what's the acceleration between 0 and 2? And these are intervals of x values, I should remind you. So between an x value of 0 and an x value of 2, where's the acceleration function? Between 0 and 2, the acceleration function it's down here. I mean, you can't see it, but it's down here. It has negative y values. Why does it have negative y values? Let me go over to Desmos, actually, for this one. So between 0 and 2, look, the second derivative is always negative in that interval. Why is it negative? Well, it's because the first derivative values are decreasing. The first derivative values, pay attention to them, they're decreasing. That's why this number is negative. So the tangent slopes are decreasing. So the tangent slopes are positive, but decreasing. All these tangent slopes over that interval are positive, but they're decreasing. The tangent slope goes from 36 to 31 to 26 and so on, all the way until a tangent slope of 0. So positive tangent slopes that are decreasing. The product of these two things, positive times negative, is negative. So the slope of the original function, like we said, it's a positive slope that is decreasing. What does that tell us about the motion of the particle? Is it speeding up or slowing down? Since the product is negative, we know it's slowing down. And we should also comment on the direction that it's moving in. And we can tell the direction based solely on the sign of the velocity. That means it's moving forward. So slowing down, moving forward. So I comment on slowing down based on the product, and I comment on whether it's moving forward or backwards based on the sign of velocity. Let's fill out another row. So between x values of 2 and 4. So between there and here. The tangent slopes are all negative in that section. Look at the first derivative, negative y values in that section. And look at the second derivative. They're also negative values. Why are they negative? Well, because these tangent slopes, which tell us the slope of the original function at any point, are decreasing from -4 to -5 to -6 to -9, so on. They're decreasing. So we have negative tangent slopes that are decreasing. So velocity is negative and acceleration is negative. The product of those two things is positive. So what we have is a negative slope that is getting even more negative. It's getting steeper. So a negative slope that is decreasing. That tells us that the object is speeding up or accelerating. So speeding up. In what direction? Since the velocity is negative, we can say moving backwards, or I think what I usually write is moving in reverse. Let's do the next interval between 4 and 6. So between here and here. Notice the original function is still decreasing. All the tangent slopes are negative. So the velocity, the first derivative, is negative. But what's happening to those negative slopes? Let's look. It's -11. As I move to the right, it goes to -10, to -9, to -8. They're going up. They're increasing. So those negative slopes are increasing. That's why the acceleration is positive. The product of a negative and positive is negative. So we have a negative slope that is increasing. That tells us that it is slowing down. I know that because the product is negative, slowing down. And since velocity is negative, I know that it's moving in reverse. Slowing down, moving in reverse. Our last interval between 6 and 8. So between here and here, the function is increasing. That's why the first derivative, the velocity, is positive. And what's happening to those velocity values? They go from 11 to 18 to 26. They're increasing. So we have positive tangent slopes that are increasing. Positive times positive is positive. So we have positive slope that is increasing. That tells us that the object is speeding up and moving forward. So example 4, I have one last example here. I think it would be beneficial for you to just give this a try. Look at each interval. So look at the interval between 0 and a, then look at the interval between a and b. Comment on the sign of velocity and acceleration in each of those intervals. And then write about the slope of the function. And maybe I'll just do the first row with you here. So in this section, the function is increasing. So I know velocity is positive. All the tangent slopes will be positive. Now, are those tangent slopes over that interval, are those tangent slopes going to get steeper or less steep? It looks like the tangent slopes are going to get more steep as you go through that interval. The tangent lines will be getting steeper, which means acceleration is positive. The product of those two things is positive, so we have positive slopes that are increasing. So since the product is positive, I know it is speeding up or accelerating. In what direction? We tell that based on the velocity. Since it's positive, that means it's moving forward. Speeding up and moving forward. Okay, try and complete the rest of the chart, and I'll put up the solution for you in just a second. So pause the video now and try it. Okay, hopefully you gave it a shot, and here are the answers. So give your answers a check. Notice, let me just take up one of these rows for you. Let's do the interval from C to D. Notice from C to D, the function is decreasing. That's why velocity is negative. Those negative slopes, they start off pretty steep and they finish at being, looks like 0. So we have negative slopes that are increasing. That's why acceleration is positive, because the slopes of the tangents are increasing. The product of the two things is negative, which means slowing down. And since velocity was negative, we know it's slowing down and moving in reverse. Okay, that's it for this lesson. I know it's a long one, but that will give us a good framework for moving forward in the course.